Greetings, Mr. Sutton here, bringing you the BC Calculus 618 Extra Practice Solutions on Logistic Growth. For this problem, we're trying to come up with a differential equation that models a certain situation. So the situation, the population of rabbits on a small island, and the population is given by P, grows at a rate, so this is dP over dt then, that is jointly proportional to the size of the rabbit population and the difference between the rabbit population and carrying capacity. Okay, so jointly proportional. Well, proportional means we're multiplying it by some constant k, and jointly proportional means we have two things that are getting multiplied by k. So we're multiplying the size of the rabbit population, which is p, so that's going to be kp, and the difference between the rabbit population and the carrying capacity, which is basically the amount of rabbits at which it's hard to get above that amount because you start running out of food and all the other things that go on. So they told us the carrying capacity is 2,400 rabbits. So then we're going to be multiplying this by 2,400 minus p. And this is just your standard logistic looking function here. So this is going to be choice D. For this problem, the weight in grams of a population of bacteria at time t is modeled by a W function, which is the solution to a logistic differential equation. And we've got some values of W, dW over dt, and the second derivative of W in this table here at various times. Basically, we just want to figure out the differential equation for W, for W, dW over dt. And if you look at these answer choices, there's a whole lot of explanation, but really we have a different equation in each of these. So it's really the equation we're most interested in, and I mean, hopefully the explanation matches. So the key on this one is realizing first off that we have a logistic function. And whenever you're trying to write the equation of a logistic differential equation, you need to know the carrying capacity. That's this 35 or 70 in these various different options here. So to get the carrying capacity, that's always going to be twice whatever the function output value is at the point of inflection. So if you can find the point of inflection on a logistic curve, twice the output level from the point of inflection, that's going to give you your carrying capacity. So looking up here, we notice that the second derivative of our function at time 2.56 is 0. Now that's key because that's usually the signal that you might have a point of inflection. Since this is logistic and you have that second derivative equaling 0, you know for certain that we have a point of inflection for W at time 2.56. Now we know that the point of inflection, again, for a logistic curve happens at half the carrying capacity. So if we take a look at the output of this function at time 2.56 and we double that will be our carrying capacity. So we need 2 times W of 2.56. Well, W of 2.56, if we look it up in the table, is 35. So twice that is going to give us 70. Therefore, we have a carrying capacity of 70, which already narrows this down then to choices C and D. So our general setup is we're going to have a dW over dt is going to equal some constant K times W times 70 minus W. We still need to figure out the K value, though, because there's two answer choices, and they have different K values that have everything else the same. So to find the K value, we have to look back at the table, and we notice in the table at time 0, so kind of our initial condition here, the value of W is 10, and at the same time, the value of dW over dt is 6. So just plugging into this differential equation, we can write dW over dt replaced by 6 equals K times that W value of 10, and then we're also going to have 70 minus 10 in that parentheses. So then this is going to be, let's see, 10K times 60 is 600K. Dividing by 600 to get our K value, we end up with 6 over 600, or 1 over 100. All we have to do now is plug that back into this general setup here. So we have dW over dt equals 100th W times 70 minus W. And that is going to be choice C. Now, if you look at the explanation, they said because the carrying capacity is 70 and the rate of change of the weight is 6 grams per hour when the weight is 10 grams. So they were basically telling us, hey, plug in 6 for dW over dt and plug in 10 for W. So everything lines up. We're going to pick choice C. For this problem, size of a population is modeled by the p function that satisfies a logistic differential equation given right here. And let's see here, we're told that p of 0 is 50. Great. What's the size of the population at the moment when the population is growing most rapidly? Well, the most rapid growth is always going to happen when the population is at half of the carrying capacity. This is a known feature of logistic functions. So to answer this question, we first need to find the carrying capacity. And to do that, we need to rewrite this equation in something that's a little bit more recognizable. So what I'm going to do is factor out this 1 over 5,000, because I like to have this in the format of Kp times parentheses 1 minus, or carrying capacity minus P form. So we need basically like some number minus just P inside of parentheses. So if I factor out 1 over 5,000 P, that's going to leave me with, well, let's see, dividing by 1 over 5,000 really means multiplying by 5,000. So 5,000 times 1/10 is going to be 500. So that's a 500 minus a p that we have inside there. And we see based off of this that our carrying capacity is going to be this 500. Now, again, this is important because the fastest growth always happens at half the carrying capacity. So when p equals half of 500, that's going to be the p-value that gives us the fastest growth. So that happens at p equals 250, which is going to be choice B. For this problem, we want to know which of the following could not be the graph of the particular solution for this logistic differential equation. So we know in general the shape of a logistic particular solution is a nice little S shape, which kind of looks like choice D here. So choice D probably is a possible solution of this thing, but we need to dig a little bit deeper. Two of the big features we always look for in a logistic curve are going to be, we have two horizontal asymptotes, one at the top, one at the bottom of the function's kind of range, the carrying capacity. We also look for a point of inflection halfway between the asymptotes. So to find all of these things, we need to at least first know the carrying capacity. And to get that, we have to put this equation here in a different form. We like to have some number minus just the output variable here, some number minus y. Right now we have something minus y over 20, and that's no good. So we're going to factor out a 1 over 20 from this parentheses in order to put it in more of a standard logistic form. So when I do that, I'm going to write 0.8y times 1 over 20. So I just factored a 1 over 20 out of there. And now inside, well, I'm going to have something minus y, because that's why I took out the 1 over 20. But what is this 1 turning into? Well, when you factor something out, you're dividing by the thing you're factoring out. So if I'm dividing 1 by 1 over 20, I'm really multiplying it by 20. So I end up then with 20 minus y inside. So this tells me that I have a carrying capacity of 20. So m equals 20, which is to say we're going to have a horizontal asymptote at 20. So I'll say horizontal asymptote at y equals 20. And now the point of inflection happens between 0 and the carrying capacity. Point of inflection is always half the carrying capacity. So our POI then is going to be half of 20, which is 10. So we're looking for graphs. We're looking for a graph that does not have a horizontal asymptote at 20, and that could not possibly have a point of inflection at 10 when we're trying to eliminate one of these as a possible solution. So looking through each of these, choice A, we've got the horizontal asymptote, and you might be thinking, well, hold on a sec, there's definitely nothing at all on this graph at y equals 10. However, we can't rule this out as a possible solution to this logistic curve, because one of the things about logistic functions is if you don't, you have to talk about what the initial value is. If our initial value of y of 0 is a number that's bigger than 20, then your logistic curve is still going to approach your horizontal asymptote, but it's going to do so from above rather than below. So A very well could be the solution to this thing if we have a y of 0 that's larger than 20. So we can't rule A out just yet. Let's go on to B. Now B, we can't see what's happening on the graph at y equals 10. We definitely have a graph that must have a y of 0 that's less than 20, so it should have a point of inflection if this is actually a logistic curve. but we can't see at y equals 10 what's going on. So it's possible that our point of inflection does happen for b just a little bit to the left of x equals 0 or time equals 0. So at time less than 0, maybe there's a point of inflection. So both choices A and B are still possibilities. Can't rule them out. Now for choice C, we can see the part of the graph that is at y equals 10, and this is clearly not a point of inflection right there. So C definitely could not be the solution to this curve because we can see what's happening at y equals 10, and it's not a point of inflection. So this is a big no right here. We're probably going to end up picking choice C. Let's take a look at D, though. Now, D is really your classical-looking logistic curve. We have the asymptote at 20. We have a point of inflection here at 10. We're changing from concave up to concave down. So D cannot be eliminated. In fact, if you were to ask which of these is the solution to this equation, you would probably pick D because it's the best answer. But we wanted the one that was definitely not the solution, and that is definitely choice C. On this free response problem, we have some liquid fertilizer injected into a hydroponics growing system. And by the way, hydroponics is the process of growing plants in sand, gravel, or liquid with no soil but some added nutrients. So we have this hydroponics growing system. Liquid fertilizer is being pumped in there with a pumping system. And the total amount, here comes the math now, the total amount of liquid fertilizer injected in there by time t is modeled by the f function. They didn't tell us what the f function looks like, but they did give us this logistic differential equation that tells us about the rate of change of the f function. So here's our logistic differential equation. And let's see here. T is in months, f is in liters, and at time 0, 3 liters of liquid are injected into the growing system. Great. So first task is actually 2 tasks, I guess, because they didn't want to have more than A, B, C, and D, so they split A up into 2 parts. First part of this, we have to find the limit as time approaches infinity of the amount of fertilizer in the system, f of t. So we're basically talking about the carrying capacity of this logistic curve, the amount that we can't really get more than that into the system. So to find that, to get the carrying capacity, and that's what this is really talking about, this limit, we just have to look at the logistic differential equation. The carrying capacity, if you have something in kf times m minus f form here, the carrying capacity is just this number that the output variable is being subtracted from in this parentheses. Because logistic curves, you always have growth that's proportional to the amount of something in a system time and the amount of something that is still to go in the system. So we have a carrying capacity of 6, and that effectively answers this question because that is going to be the limit of the amount of stuff in the system is the carrying capacity. Now for this next part of the problem, they're asking for the limit as t approaches infinity of the derivative of the function of this differential equation here. So the whole idea is that as you go to infinity, you're hitting this carrying capacity. You've got this horizontal asymptote limiting how much of something you can actually get in a system. So as you get closer and closer to that asymptote, your function grows more and more slowly so that it's not crossing the asymptote. So eventually your slope is approaching 0 at that asymptote. For this part of the problem, they want the value of df over dt when f is increasing most rapidly. So basically asking us to maximize df over dt. So in order to justify all of this, the way these logistic curves work, you have your fastest growth at the point of inflection, which always happens at half the carrying capacity. So in order to figure out the f value that maximizes our growth, I'm going to do half of my carrying capacity of 6, which is just 3. So if I plug 3 for f into this differential curve, that's what's going to give me the value at the time when f is increasing most rapidly. So let me go ahead and do that. That's going to be 1/3 3 times 6 minus 3. And that's going to be, let's see, 1/3 and 3 cancel, so it's just 6 minus 3, which is 3. And what's the units on this going to be? Well, again, they wanted the value of df over dt. F is measured in liters. Time is measured in, what did they say, months. So this is going to be 3 liters per month. For this part of the problem, they want the second derivative of f in terms of f, so this ought to be interesting. We're going to start with the differential equation here, because this is at least the first derivative of f. So before I actually try to take the second derivative here, just to avoid having to use the product rule, I'm going to distribute this 1/3 f. So that's going to give me 2f minus, this will be 1/3 f squared. And now let me just use my power rule here. So this is going to be 2, but f is actually its own function of time. So we have to write this as 2 df over dt. And then here we've got 2/3 f times df over dt. So we're differentiating implicitly here. So this is at least some kind of derivative. Unfortunately, it's not the kind they want. They wanted the second derivative in terms of f. So in order to get down to that level, I'm going to have to replace the df over dt with the stuff that it equals up here. Now I could do this right away, but that's going to be kind of messy. So one thing I am going to do, I'm actually going to factor out this df over dt just so I only have one of those kicking around. So that'll leave me with 2 minus 2/3 f in a parentheses. And now I'm just going to replace this df over dt with 1/3 f 6 minus f, like so. And now I have their second derivative in terms of f. For this final boss battle on this question, this is also a two-parter. First part, they want us to use Euler's method starting at time 0 with 2 steps of equal size to approximate the total amount of liquid fertilizer injected by time 1 month. And since we're using 2 steps of equal size and we're going from 0 to 1 for the input, that means we have to go by increments of 0.5. So to get from 0 to 1, the first step along my way, I have to figure out f of 0.5. This is going to be f of 0, approximately f of 0, plus f prime of 0 times my step size of 0.5. F of 0, what is that? Well, they told us at time 0, 3 liters of liquid are injected into the growing system. So that's just a 3 right there. And then what's f prime of 0? Well, for that, we're going to have to use our differential equation. So that's going to be 1/3 times the value of f at time 0. So we're not plugging 0 in for f. We're plugging in whatever f equals at time 0 in this differential equation. And again, that was 3. So this is going to be 1/3 times 3 times 6 minus 3. So let's see, 1/3 of 3 is just 1. 6 minus 3 is 3. So f prime of 0 is 3. And we also have that 0.5 we're multiplying by. This is a no calculator question, so we are going to simplify this as we go. Otherwise, it's going to become unruly pretty quickly. So we've got 3 plus 1.5, which is 4.5. Moving on now, we're going to try and figure out f of 1 using this value that we just got for f of 0.5. So f of 1 is going to be approximately equal to f of 0.5 plus f prime of 0.5 times our step size of 0.5. F of 0.5 is approximately what we just found here, 4.5. F prime of 0.5. So f prime of 0.5, we have to do 1/3 times the value of f at 0.5. We just found that value approximately. That's going to be about 4.5. So this is 1/3 of 4.5 times 6 minus 4.5. And we can simplify this a little bit. 1/3 of 4.5 is 1.5. We're multiplying that by, coincidentally, 1.5. So 1.5 times itself, well, I know that 15 squared, I just happen to know that that's 225, so this is 2.25. And that'll be our f prime that we're using here. I guess you could do that out by hand if you really needed to. So let's see here. We've got 4.5 plus 2.25 times 0.5. You could actually stick units on this one and call it done, but if you wanted to simplify it, half of 2.25 is going to be, let's see here, 1.125, and 4.5 plus that is going to be 625. There we go. Okay, and that's going to be in liters because we were approximating the amount the value of F in the system, which is measured in liters. It's the amount of fertilizer. So the second part of this, we want the approximation. We want to know if this approximation here, which is all that is an over or under estimate. Now this one's a little bit tricky. To figure out over or under for Euler's method, it's really the same criteria as over or under for a tangent line, because Euler is just a bunch of tangent lines. So we need to know at the point that we're approximating, or at least the interval over which we're approximating from 0 to 1 for time, is the curve itself concave up or concave down? Knowing that will just give us our answer. So which one is it, concave up or concave down for this point? The key on this is just remembering with logistic functions that you have that point of inflection at half the carrying capacity. And just remember back a little bit, our carrying capacity was this 6 that we picked out of our differential equation. Half of that was 3. So at f equals 3, your graph is changing from concave up to concave down. It starts to slow down at f equals 3. So what time do we hit that at? Well, here's another key. They said that at time 0, 3 liters of liquid fertilizer injected into the system. So that half the carrying capacity, that point of inflection, happens at time 0. Since that's happening at time 0, that means that everything after time 0, our graph is going to be concave down. It's going to be on that concave down part of the logistic curve after the point of inflection. So that means specifically for this problem, between values of f from 3 to 6, we're going to be concave down. We're going to be concave down on the interval, the t interval, from 0 to 1. So since we have a concave down function and we're using basically a tangent line on it, that means we are going to overestimate the true value of f of 1.